Hello everyone, I hope you're all doing well. In today's lecture, we're starting into our last section of the textbook, so section 6, where we start looking at balancing research priorities. So how do you actually make a decision as to what kind of research you can and can't use in a particular situation? So chapter 13, which is today's topic, is going to focus on quasi-experiments and small n designs. So we're going to break it up into those two sections. So a quasi-experiment being not quite experiments, things that are set up very similarly to experiments, but don't quite meet all the criteria that make it an experiment. And then small n designs are just when we're studying only a few individuals to try and understand something. So we will start with our quasi-experiments. So we're going to start by looking at two examples of independent groups quasi-experiments. So we're going to talk about two of the major types of quasi-experiments with independent groups and then repeated measures designs. And they're going to be very similar to the independent groups and repeated measures designs that we've looked at for actual experiments. So we're just going to have the modifications where they aren't quite experiments. And so we'll discuss examples of each of those and explain why they aren't quite experiments. Then we want to get into the question of internal validity in these quasi-experiments. So if we are concerned with establishing causation, if these aren't quite experiments, then we're going to have to look at their internal validity. Is there something going on within these not quite experiments that is not allowing us to have high internal validity? And just the nature of these not quite experiments makes them more vulnerable to threats to internal validity than true experiments, just because they're not experiments. We can talk about balancing our priorities, so why you should use one of these methods over an experimental method. When is it okay? When does it have to happen? Pros and cons, that sort of thing. And then we can start comparing these quasi-experiments to correlational studies, because some of the methods we're going to talk about will be very similar to correlational studies. And it's kind of hard to tell the two apart. So that's what we have to look forward to in the next set of slides. So our two examples when we're starting off with these independent groups quasi-experiments, we're going to look at the psychological effects of walking by a church and the psychological effects of cosmetic surgery. And both of these experiments, or quasi-experiments, have sort of the same kind of design, and we can call it a non-equivalent control group design. So because it's an independent groups setup, there are different participants at each level of the independent variable. So we're going to have different groups for both levels of our independent variable. We're also going to have at least one treatment group and one comparison group, kind of, sort of. But unlike in true experiments where we would randomly assign people to be in either the treatment or the comparison group, in these quasi-experiments, and specifically the non-equivalent control group designs, the participants aren't randomly assigned. So maybe they choose which they are, or just by the nature of their being, they fall into one category over the other. And what that means will become clear as we go through these two examples. So we'll start with walking by a church. And so in this experiment, this was done by LaBeouf and colleagues back in 2012, and they basically approached 99 people who were passing by either a religious or a non-religious landmark in one of two cities. So were they walking by a church, or were they walking past a government building? And so they specifically selected people using a non-systematic sampling approach. So they were trying not to be biased and only approaching, say, people that they were comfortable approaching. They would approach every 10th person they saw no matter what, or some other systematic method. And they specifically approached only people who were passing by, but not entering or leaving the building. They just wanted to see if walking past a church versus walking past some other landmark-esque but not religion-associated building would alter people's perceptions and views. So they had each person that was selected from the people passing by. They had them complete a short questionnaire, and they specifically asked questions about their religiosity, their political views, and what they were really trying to get at, which was their attitudes towards a specific variety of social groups. And so the idea here is that in other studies, when people are primed or exposed to religious associated words, they tend to sort of close ranks. So they tend to be more negatively acting or negatively perceptive of outgroups. So for religious groups, that would be anyone who is not part of that religion. So if someone identifies as Christian and they are primed with religion-associated words, their opinions expressed about other groups tends to be more negative. And so the whole purpose of this study that we're talking about with people walking past churches or walking past non-church buildings was to see if just being near a religious structure could cause that same kind of priming effect. And so in this study, we have an independent variable, which is the type of building that people are walking past. And there were several dependent variables, basically the things that they were measuring with their survey. We are pretty much just going to talk about attitudes towards a variety of social groups, but on the screen here we actually have all of the measures that they took for their dependent variables. And so on the surface, we have this independent variable. They walked past a church or not a church, and they were measured on all of these dependent variables. It seems very experiment-like. But because people were not randomly assigned to walk past a church or not a church, this is actually a quasi-experiment. So because there was no random assignment, because we're not choosing what building they walk past, this isn't quite an experiment. And so in this case, it's an example of a non-equivalent control group, specifically a post-test only design. So we're using this non-equivalent control group, plus the fact that we're only testing once after they had walked past that building. So we're putting them all together, and this is a non-equivalent control group post-test only design. And so we're specifying all of that because the participants were not randomly assigned to groups, and they were tested only after they had been exposed to one level of the independent variable or the other. So they were only ever exposed to one level of the independent variable. They only walked past a church or not a church, and they weren't randomly assigned to do either of those. All right, so that's all of our experimental setup, or pseudo-experimental setup. And so for our variables, they looked at belief in God, their religiosity, political conservatism, so how conservative are their political views, warmth towards Christians, warmth towards foreigners, warmth towards Arabic people, warmth toward African people. And so this column here is showing the people who walked by a religious building or landmark versus walking by a non-religious building or landmark. And these asterisks here are showing that the difference between religious buildings and non-religious buildings is statistically significant. So most of these things are showing a statistical difference. So belief in God, not so much, and warmth towards Christians, not so much, but pretty much everything else was a statistically significant difference, and as we would expect from the other experiments that I explained very, very briefly, where priming with just religious words caused this sort of effect, we're seeing that people are more critical of outgroups, of people who are not their own group, when walking by a religious building or landmark. Now, we're going to come back to this experiment at least once during this chapter. I believe we'll talk about some expansions and some critical thinkings about this. But for now, we'll just leave it as explaining the setup there. For our second example, we can look at the psychological effects of cosmetic surgery. And since the setup is going to be fairly similar, we can move through this one just a little bit quicker. So the researchers, Margraf and colleagues in 2013, they wanted to compare the self-esteem of people who underwent cosmetic surgery and people who only considered cosmetic surgery but didn't get the surgery. So a lot of people choosing to have plastic surgery are doing so to enhance their self-image or increase their self-esteem. They want to feel better about themselves. And so these psychologists wanted to see if these effects actually occurred. Do people who get cosmetic surgery experience an increase in self-esteem and self-image? Are they happier with who they are and how they look? And so again, we really cannot assign people to have or not have plastic surgery. That is a very ethically gray area. So you would have to conduct a quasi-experiment where people who underwent cosmetic surgery were people who were going to have cosmetic surgery anyways. And for their comparison group, they used people who had registered at the same plastic surgery office because they were interested in plastic surgery, but they elected not to undergo the surgery. So they had the same basic idea of maybe I would like this surgery, but they didn't go through the actual surgery. And so once they had these two groups of people who had plastic surgery and people who didn't, the researchers surveyed the participants at 4 different time points. So before they underwent surgery, and then 3 months afterwards, 6 months afterwards, and a year after their surgery. So this time, instead of just a post-test only design, now we're looking at a pre-test, post-test design. We're measuring multiple times during the course of this pseudo-experiment. And the researchers measured 3 different dependent variables here. They looked at self-esteem, life satisfaction, and self-reported general attractiveness. So how attractive do they think they are? We're only going to be looking at a self-esteem score on this page, and then I believe we go into life satisfaction on the next page. Oh, actually, we do have all 3 just on different slides. So ignore that. Okay, so here we can look at, for the first, self-esteem score. So our first of the dependent variables on our y-axis, and then our 3 different time periods after surgery, and then our baseline before surgery on the x-axis here. And then we have green versus orange for the surgery group and our comparison group. And so here, our surgery group has a sort of flat line showing a somewhat positive slope, almost flat, but a little bit positive slope here. Whereas the comparison group, they started with the same baseline self-esteem score, but the comparison group seemed to have a reduction in that self-esteem. So after a year, our surgery group had a higher self-esteem score than the comparison group did. And the surgery group actually had a higher self-esteem score a year after surgery than they did before surgery. So this is giving us some evidence that maybe cosmetic surgery caused a rise in self-esteem. And we can see kind of similar trends across the other dependent variables. So our life satisfaction rating shows this divergence here where our surgery group is higher than the comparison group, though this time they didn't start at the same point, which can cause some critical thinking later on when we're evaluating this study. And then for general attractiveness, we're seeing that they're starting fairly close together, and the surgery group is again higher than the comparison group. But we're seeing across 3 different measures, we're showing that, yeah, there is still this difference where the surgery group has increased these levels of self rating of attractiveness or self-esteem or any of those things. They seem to be doing better. So maybe cosmetic surgery is causing a rise in self-esteem. Now that can we say it has caused that rise is something we can evaluate in a little bit. But like we said at the very beginning, they're not all going to be independent groups. We can also have repeated measures, quasi-experiments. So basically the types of experiments that we've talked about, there are ways to have quasi-experiments where some aspect of the experiment can't happen, so we specify that they are quasi-experiments. So these are going to be the same or analogous to our repeated measures designs for true experiments. So all of our participants experience all levels of an independent variable, but unlike those true experiments, that independent variable is not manipulated by the researchers. It sort of varies on its own, and we just make use of that. So our first example of this kind of quasi-experiment is looking at food breaks and parole decisions for judges. So people generally agree that legal decisions like granting parole should be made very objectively. So judges should be able to critically weigh the pros and cons of granting parole and make a very level-headed and uninfluenced decision. So any kind of extraneous factor that could influence that sort of decision would be of concern. So another research team, this time Dan Ziger and colleagues in 2011, set out to investigate the effects of food breaks on parole decisions. So they looked at a bunch of different judges, and judges are like any worker. They have periods throughout the day where they stop judging and they get to go and have a break. They get to eat, they go for lunch, they have a snack break, whatever, during their day. So all of the judges received the same breaks. So they would have like a morning snack break, a lunch snack break, and then they'd go home in the evening. And this experiment was looking at an Israeli court setup. So the prisoners that were being judged, that were having their paroles decided for or against, came from 4 different Israeli prisons. And parole was rejected about 65% of the time on average. But whether or not the prisoners came before the judge, before a break or after a break, actually ended up having a pretty major influence on whether they were given parole. So if we look at our graph over here, we have our dependent variable, which is the proportion of favorable decisions. So how often were people actually granted parole? So overall, there was a reject rate of about 65%, which would put us around this line here. So if this is favorable, then there is a, here. If I could do math, that would be helpful. So if 65% are rejected, then 35 are accepted. So our average line would be here, which kind of makes sense, but we're seeing that there are spikes where many more people are given favorable parole decisions. And when we're looking at the bottom here, so this is just time of day. So start of the day, and then we have these dotted lines are showing when the judge went on break. So first thing in the morning, they probably would have had breakfast before coming to work. Then they work for a while. then they go on their morning break or their lunch break, however they decide to do that. Then they work again, and then they have another break in the afternoon, and then they work again. So that's what we're looking at here. And we're seeing that after each of these breaks, there seems to be this rise in favorable decisions and a sharp drop-off in those favorable decisions as we get further and further away from having eaten. And this value is presented for multiple judges. So they basically averaged the numbers across all judges, across all the days that they surveyed, to give us this line here. So this isn't just an individual's data, this is everyone's data all put together. And so this setup, this design, is called an interrupted time series design. And so this is a repeated measures study because all of these judges are being measured throughout the course of their entire day. They are constantly recording what their decisions are at what time of day. And it's an interrupted measure because they have these breaks where they go for food and there's no measure taken during those breaks. But we do measure before and after the breaks and basically all the times other than the breaks. So that's where the name comes from. And from just looking at this, we can tell that the proportion of favorable decisions is high at the start of the day or soon after a food break, but declines very quickly until the next break occurs. So the researchers proposed that this happens because the break provides time for mental rest, the food restores their blood glucose levels, and in the study, they made a causal claim about these results. So saying that they show that the breaks are causing the favorable decisions to be higher right afterwards. And again, we'll evaluate whether or not that's a valid claim to make. Our next example of these repeated measures, quasi-experiments, is looking at the impact of healthcare laws. So in 2010, the US federal government enacted what's called the Affordable Health Care Act, and that required all citizens to acquire health insurance or face fines. So 4 years before that date, Massachusetts had enacted a very similar law, but it only applied to the state of Massachusetts. So at the time, a team of public health researchers wanted to evaluate if that Massachusetts law had made any difference in people's access to healthcare. Because if they could learn something about how it had worked for Massachusetts, then maybe it would shed some light on what might happen in all of the US. So in this case, the researchers acquired data from a massive sample of adults, and they specifically targeted non-elderly adults. So I believe their criteria was 18 to 65. But they got a sample of 178,000 people. So some of them lived in Massachusetts, which was their target state, but they also got a comparison group, others who lived in neighboring states in New England, so in the same area, but not within Massachusetts. And those other states didn't have the same kind of health insurance requirements. So the idea here being that the thing that differs between the two groups is whether there's a law that requires health insurance or not. So they have their comparison group there. And so the researchers used data from a yearly national survey that asked people whether they have insurance, whether they have a personal doctor, or if they had ever gone without medical care because they couldn't afford it. So the idea here being that that law that's forcing people to have insurance should encourage them to also have doctors and make sure that people don't go without medical care because their insurance means that they can afford it more often. And so if we orient ourselves on this figure here, we're going to just look at the percentage of people surveyed that said they were unable to see a doctor due to cost. So that's our dependent variable here, though they did measure others, as we just said. And then along our x-axis, we have the year, so these are different periods in time. And because it's a repeated measures design, they were measured repeatedly. And so our green is our control group from nearby states, and the orange is going to be Massachusetts, our state of interest. And so before the law came into effect in Massachusetts, the two lines are fairly close together. And then after that time, we see that the green line holds fairly steady. There's a little bit of variability all the way back here, but this way it's pretty flat. But the orange line takes this dip downward away from the green line. And so for interpreting this, fewer people reported that they couldn't see a doctor because it was too expensive. So the question here, as you might expect, is, does this quasi-experiment demonstrate that that new law caused people to better afford healthcare? And again, we will come back to that. Now, all four of those examples on the surface look quite a bit like any of the experiments that we had talked about in previous chapters. We have independent variables, dependent variables, control groups, and treatment groups. And any time that we're trying to look at causal relationships, like we have been with our experiments, internal validity is one of our major concerns. So quasi-experiments are subject to the same kinds of threats to internal validity that we talked about in terms of true experiments. And due to the design of these quasi-experiments, sometimes we have to consider these threats in novel ways. So it isn't going to be exactly the same as when we applied these to our experiments, but you will see some similarities and some crossover. So we'll go over this hopefully fairly briefly. And so for each of these, because they're the same sort of threats that we've already talked about, I'm not going to spend too much time explaining what they are, but we will talk about them very briefly. So starting with our selection effects, this specific threat has to do with unaccounted for differences between groups. So it's really only going to be relevant in independent group designs. So not necessarily the purely repeated measure designs. Those are going to be not as much of a concern. But for our independent group designs, selection effects can be a problem. So if we think about our cosmetic surgery example, there could have been differences between the people who had the surgery and those who did not. So what if the people who were interested in cosmetic surgery but decided not to have surgery, most of them maybe did it because it was expensive? So if the people who got the surgery were more financially stable than those who didn't get the surgery, well, that financial well-being might have explained some of the things that we were looking at. So for example, that difference in overall quality of life could have been explained by the people that got the surgery also happened to be more wealthy. But for the critical evaluation of that particular study, the researchers took that into account specifically by using matched groups. So we didn't mention the specifics of how they chose their control group, but they used a matched group setup in which they took into account a lot of demographic variables, things like age, gender, body mass index, or BMI, as well as income, to make sure that their control group was as close as possible to their treatment group. So they wanted to account for as many possible third variables as possible, and include those in their analysis. So by matching the two groups, they weren't really concerned about selection effects because they were able to control for so many things that could have been third. For our next point, our design conflicts, here we need to be on the lookout for extraneous variables that might influence the results of your study. So specifically, we care if some outside variable is accidentally and specifically systematically varying with the levels that are targeted by our independent variables. So if there's some kind of systematic variation that happens to be influencing the results of our study, we might have a design conflict. So if we go to our parole example, what if the prisoners who went to the judges right after lunch were systematically varying in something like the degree of their crimes? So what if the people who came in after lunch were not serious criminals? And that would explain why there was that higher rate of approved parole, because they were guilty of less serious crimes and they could be paroled. And so in that case, the researchers, again, were very careful to consider that possibility. So they specifically measured what the criminals were convicted of, how long they had been in jail for, if they had been in jail multiple times, and they took all of those factors into effect and ruled out those kinds of conflicts. So that is an example of what the design confounds could have been, but they weren't a problem for that specific example. For our third option here, we have that maturation threat. And these threats occur when in an experiment or quasi-experiment design that has a pre-test and a post-test, that the observed change emerged spontaneously over time. Again, in our cosmetic surgery example, the participants who had surgery improved in their self-esteem and life satisfaction and general attractiveness scores over time. So maybe that was just a natural maturation of those variables. Maybe they would just start feeling gradually a little bit better about themselves over time. So if you are worried about a maturation threat, you'd be asking yourself, okay, so was that improvement because of the surgery, or was it because of a spontaneous maturation? And again, that design included a comparison group. So the same way that we counteracted maturation threats when talking about pure experiments, same thing here. Having a comparison group showed that both groups didn't show that same increase over time. In fact, our comparison group got slightly worse on those variables over time. So because of that setup and what our results look like, we wouldn't be as concerned about maturation as an internal validity threat for that particular study. But that's how we'd go about evaluating it if we were concerned about it. And then the last one for this slide is the history threat. And so history threats, if you recall, happens when an external historical event happens for everyone in a study at the same time as the treatment. So another external variable that is happening that could be influencing your group. So again, with that history threat, you're not quite sure if the outcome's been caused by your treatment or if it's been caused by this external event. So in our Massachusetts health insurance study, that residents' ability to afford medical care, having fewer people not going to a doctor because it was expensive, might have also corresponded to an economic upturn. Maybe coming out of a depression made it easier for people to afford going to the doctor. And then maybe it had nothing to do with the enactment of that law. But again, this particular study included a comparison group, and both groups didn't show the same pattern in improvement there, so the researchers could actually rule out history threats because of that comparison group. So very, very similar to what we had talked about previously. So continuing on with our threats to internal validity, we can talk about regression to the mean. So that's when your extreme findings is at the beginning caused by those random factors that all sort of line up together and cause an extreme measure. And the likelihood of all of those factors happening to occur together for a second time when you measure them again is very low. So the extreme findings tend to become less extreme over time. And so from the nature of this setup with regression to the mean requiring a change between two measurements, this has to be for a design that uses more than one measurement. So for example, a pre-test, post-test design. So if we look at our cosmetic surgery again, we can rule out regression to the mean as causing the changes within our surgery group. And the first reason that we can rule that out is because the researchers didn't select our surgery group because they had unusually low scores at pretest or unusually high scores at pretest. So they used another method of selection, which is a good idea. And the second thing is, if regression to the mean was the explanation, then the individuals in the surgery group would have started out differently than the comparison group. But in most of our measures, they started out either pretty close to the same or even higher, but not extremely so. So by looking at the data and critically thinking, and again, comparing to a comparison group, you can rule out regression to the mean. We can talk about attrition threat. So again, these pre-test, post-test designs, attrition is when people drop out of the study. And it's specifically a problem if there is a systematic dropping out of people. So if you lose all of the people who scored really high on one of your dependent variables or who scored really low on your dependent variables, it can mess with your results. And so, like, if we look at the cosmetic surgery, you can look at people who dropped out of the study over the repeated measuring. If they were all people who were low in self-esteem, or were they all high in self-esteem? And this is one of those things that the researchers can look at critically themselves just by analyzing their data. When we talked about this for experiments, I mentioned that some researchers can afford to just remove incomplete data. So if someone drops out from the experiment, you remove them from the pre-test and the post-test. You take out any data where it isn't a complete set. You can also use statistics to determine if those people were systematically different from the rest of the sample, or if there are ways you can sort of fill in the missing data if you have to, but that's a little bit more complicated than I think we should get into. But the take home here is that if you do your due diligence as a researcher, you can make sure that attrition isn't a problem. We can look at our testing and instrumentation threats. So this is, again, whenever you're measuring your participants more than once. So are you having a problem with your participants? Are you having a problem with your measuring materials or your measuring instruments? And in this case, you can kind of treat it the same way we did in experiments. So critical thinking, having a comparison group, and that sort of thing. Oh, I did not mean to scroll over there. I meant to scroll in my notes. As you can tell, we're starting to group these together because these ones aren't as important to talk about individually as the ones we started with. But for our observer bias, demand characteristics, and placebo effects, these threats to internal validity all have to do with human subjectivity. So we have to care about how people are interacting with things. And the same way that we would deal with a lot of these in the true experiments, you can set up some kind of disguise or masking of the true intention of the study to try and stop some of these things. So instead of asking people to answer your questions about your perceptions of outgroups or non self-identified races, you could just say that you have a series of questions. Maybe don't give away what you're studying. So treat it more like a real experiment. And so by doing that, you make it harder for the participants to figure out what the study is about. You can also make sure that the people doing the observing maybe don't know what the study is about. Those sort of things are all useful for the same reasons we've discussed quite a few times at this point. Okay, so that is a lot about internal validity threats. And at this point, we kind of get to that question of, okay, well, if these quasi-experimental studies are so vulnerable to internal validity threats, possibly even more so in a lot of cases than our experimental or full experiments, why would a researcher actually want to use one? And we have a couple of examples. So for real-world opportunities, you basically are making do with what you have available to you. So the team looking at health insurance wouldn't have been able to randomly assign states to require health insurance or not, but they took advantage of the opportunity that having that law enacted in a single state provided them. Same thing, you can't manipulate people into having surgery or not having surgery, but you could take advantage of what happened in that real world setting and measure accordingly. So sometimes you're just making do with what's available to you. For external validity, when we run true experiments, we're usually running them in a lab, in a very controlled environment. But as we've seen with a lot of our examples here, these quasi-experiments are run in the real world. And that real-world setting can help enhance our external validity because we're not so far removed from the environment. So the likelihood that the patterns we're observing will generalize to other situations and other individuals is a little bit higher. Again, depending on the specific setup, but overall we can get some increased external validity. The idea of ethics is one that's probably already occurred to you. So a lot of questions of interest that researchers end up using these quasi-experiments for are things that they can't ethically manipulate in a true experiment. It's not ethical to assign elective cosmetic surgery to people who don't need it or who don't want it. It's not ethical to withhold insurance benefits from people in randomly assigned states. So these quasi-experiments are a more ethical option that still allow you to study those kinds of questions. And then for our last point with the construct validity and statistical validity, usually these quasi-experiments are very well designed. They have excellent construct validity for that independent variable. So in our religious landmark study, people actually walked past a church or did not walk past a church. It was pretty clear cut. So in the judge decision-making study, the judges took a break when they said they took a break. So these things are very easy to measure, and you have fairly decent internal, you have very good construct validity, especially with those independent variables. In terms of statistical validity, for the same way that we can evaluate statistical validity with experiments and anything else, you can actually run the statistics. And if you run good statistics, you can get answers to questions like, how large were the group differences? So the effect size. Are the results statistically significant? What were you looking at? And especially in the case of some of the quasi-experiments we've seen here, with large N's, with very large samples, you can have some pretty good statistics run on that data. So you end up having fairly high construct and statistical validity, which is pretty great. So those are reasons why you might want to run these quasi-experiments. And then for the last part of the quasi-experiments is asking the question, are these quasi-experiments the same as correlational studies? So on the surface, some of these quasi-experiments may have sounded very, very similar to the correlational studies we've talked about earlier on in the textbook. And yes, they do have a lot of characteristics in common. So specifically, we're going to see a lot of overlap with quasi-experiments that use independent group designs. Those look very similar to our correlational studies where we were measuring two different variables and then running our regressions. And so in the correlational studies, as well as in our quasi-experiments, you're comparing two or more levels of an independent variable in order to predict one or more dependent variables. And independent and dependent are a little bit harder to assign with some of the correlation stuff, but it's the same basic idea. Our correlation studies and these quasi-experiments don't use random assignment. So you're just measuring these things. You're not actually manipulating them using that random assignment to put people into groups. And you're not manipulating the independent variable. So the textbook talks about the distinction between correlational studies and quasi-experiments is that quasi-experiments tend to be a little bit more manipulated or a little bit more adjusted by researchers. So researchers conducting these quasi-experiments have a lot of techniques that they can use to try and enhance their internal validity and maybe give some extra evidence for causal claims. That being said, depending on how it's framed, some of these could be either a quasi-experiment or a correlation study. And that's fine. Because a lot of the stuff that we've been talking about specifically for quasi-experiments are still applicable to correlational studies, just as a lot of the points we've talked about are applicable to the experimental studies. So the textbook specifies that, so for the correlational studies, researchers would simply select some people, so they'd conduct a survey or seek out their sample sort of less actively. They'd measure their variables, test the relationships, and that would be that. But in the quasi-experiments, the researchers would obtain their groups by targeting specific locations, so they'd be a little bit more active in going out to find people that fit their specific intention with this study, or they might seek out comparison groups specifically to try and match their treatment groups. They might try and seek out specific situations that would give them a good comparison. Again, more active in quotes here. But that being said, I'm not going to give you an example and say, is this a quasi-experiment or is it a correlation? Because that distinction doesn't really matter. What we care about is our interpretation of what's going on, as opposed to telling the two apart. All right, and on that wishy-washy note from the textbook, we're going to move into the second part of this chapter, which is talking about small n designs. So what happens when we're studying only a few individuals? And so when we're talking about n, we're talking about the number of subjects or the number of participants in a study. So small n studies have very few participants. And sometimes we can encounter situations where we only have one individual. So if you have a case study, you have an n of 1. And so if we look at some of the big differences between our large and small n designs, in large n designs, you have groups of participants. The data from an individual participant doesn't really matter. So you don't care about one measure, you care about the pattern across all of the people you measured. So you're going to group all of their data together and study it as a grouping. So you're going to present your data as group averages. In a small n design, each participant is treated separately. Sometimes you're going to care more about just one measure than about sort of multiple individuals because you don't necessarily have multiple individuals. These small n designs are almost always repeated measures designs. because the researchers are trying to observe that person or animal in a bunch of systematically designed conditions. So small n designs are set up to give you the most detailed understanding of what's happening using a single individual. And so when you're presenting the data from these small n designs, we care about each individual data and each individual data point. So instead of grouping things together and averaging, you're going to focus on individual points. And we can talk about a very famous case study that's popular in psychology by looking at studying human memory. So Henry Molaison, or HM, suffered from debilitating seizures due to epilepsy. And because these seizures were so debilitating, he opted to have a surgery done to try and stop the seizures from spreading. So they had a surgeon who removed the front half of his hippocampus on both sides, both hemispheres of his brain. And the surgery was a success in that it stopped his seizures. The problem was it ended up causing really severe memory loss. So he couldn't form new memories. He ended up with anterograde amnesia. So he could remember things that happened before the surgery, but he couldn't form new memories. And so because of this extreme situation, he became a person of interest for a lot of psychological researchers. So perhaps you've heard of Scoville or Milner, and they studied HM for years and years and years. And so by studying him, they figured out that this bilateral hippocampal lesion, or removing most of his hippocampus, didn't affect intelligence or personality. It just affected his ability to form new memories. So over the course of 40 years, they wanted to figure out what changed or what abilities did HM lose because of this removal of specific parts of his brain. And the tasks that they developed, these repeated exposures to different tasks, these lots of measurements of this one individual's performance, they helped document the biological separation between declarative memory, knowing that something has happened, something you can talk about, and non-declarative memory, knowing how to do something. They figured out that those are two separate systems because of HM. And this image here is an example of how they figured that out, where they would go into HM, they would say, I have a task for you. I want you to trace this star by keeping the pencil in between these two lines all the way around. And they would do this every day or multiple times a day. And each time they would bring it to him, he'd say, oh, that's such a hard task. I'd never know how to do that. But despite the fact he couldn't remember that he could do the task, his body or his hand seemed to be able to know how to do it. So he could form the memory of how to trace inside the lines around this star, but he couldn't form a memory of actually having done it before. So his non-declarative memory was fully intact, but his declarative memory was not intact. So even though he could claim to have never done this task before, he became very, very good at it. And so here I am talking about a single case, and this is helping us show that declarative and non-declarative memory are two separate systems. But how much weight should we give to these case studies, to these situations of research on special cases of ends of one? So how much do we trust the outcome of these studies? And so this is where we start talking about balancing our priorities for these case studies. In terms of experimental control, case studies are amazing at advancing our knowledge because the researchers are specifically using very careful research designs. So they are devoting lots of time and effort, and they're trying to think through all of the possibilities to come up with very specific tasks, very precise tasks, like tracing that star, that test the difference between declarative and non-declarative memories. So if you carefully design an experiment, if you have good experimental control, you can pick apart different effects and figure out what's going on. So because of the empirical strengths of these studies, you can actually make some conclusions. So with HM, in some cases, they would test his ability to remember things like strings of numbers or images, and they could compare his ability to people who were the same age, the same race, the same gender, the same body type, but didn't have brain damage to get a comparison. Still small n, but there was something to compare against. They could also, like I said, deliberately design those tasks to isolate different pieces, and they could conduct multiple measures. So they wouldn't just have him trace a star, they could have him do multiple tasks that would test non-declarative memory versus declarative memory. And if they get agreement between multiple types of tasks, then they could be even more certain of their conclusions there. The other thing to consider is that these special cases, these case studies, studying individuals, it usually happens because just like our quasi-experiments are letting us take advantage of things happening in the wild, these case studies are letting us study very specific and special medical cases. So it is excruciatingly rare to find someone with the same kind of brain damage as HM. So it would be almost impossible to study this particular setup in more than one individual. So we kind of have to take into account the fact that we're studying an N of 1 because there is only one. That's the only thing that we can do. And so when we're doing that, even though with our experimental control, our manipulations, trying to replicate by using multiple studies and comparing to others, we're doing the best we can, but we also keep in mind the fact that this is coming from a single case. So maybe we're not going to apply this to all people unless we can find maybe a second or third person who has similar damage that we could find similar results in. And that brings us to some of our disadvantages of small n studies. So still with HM, his cerebellum was actually damaged because of the anti-seizure medications he was on prior to his hippocampus being removed. So even though we cared about the fact that the hippocampus is involved in long-term memory formation, we couldn't actually be sure that what we were seeing was due to just the hippocampus. We couldn't be sure that there wasn't some involvement of the cerebellum. So you would have to start looking at sort of other things that could be going on. So because we had multiple types of damage, there was some difficulty in narrowing down what was specifically responsible for what we were observing. So we had some internal validity issues where we weren't sure what the driving force was behind our measures of our dependent variables in all of these studies. So you have to keep that in mind. Another disadvantage involves external validity. So people in these small n studies probably don't represent the general population very well. So HM was specifically someone who had been suffering from epilepsy, who had damage to his cerebellum, and had his hippocampus removed. So there are very, very, very few instances of that happening in anyone else ever. So you can't really generalize to a larger group. It's very difficult to be sure that what you found would apply in all situations. And clearly, it would be unethical to create a situation that matches that to test your results to make sure that it would generalize. So we're left with a lot of limitations that we have to be aware of. And sometimes that's just what you have to do. Another situation that we see these small n's, other than studying people with abnormal brain damage or special situations, we also see these small n studies used a lot to evaluate efficacy of a treatment or an intervention. So trying to help someone who has some kind of problem where we think that a specific action or treatment could help with their problem. So we can look at 3 different studies that had different kinds of treatments trying to modify behaviors of individuals. And we can talk about the methods that they used to help be more certain that what they were seeing is what they hoped that they were seeing. So trying to improve our internal validity here as well. So the first example, we can look at a stable baseline design. So that is what we have up on the screen here. And this setup is going to be one where the researcher observes the behavior of interest for an extended period of time. And this period of time, they're not doing anything but observing. So they're establishing a baseline. What is the natural behavior before any kind of intervention or treatment is introduced? So on our graph here, we're looking at percentage of words recalled, because we're going to be looking at word recall in an individual who had Alzheimer's. And so the baseline is that she would recall very, very few words on her own. So they had 5 measures in 2-week intervals. So across a period of 10 weeks, they came in and measured this individual's word recall, and it was very, very poor, and it was consistently poor. And so once they were sure that they had a stable baseline, then they could introduce this treatment. And so here at this 10-week mark, I guess, so the 5th time they came in at a 2-week interval, they taught this Alzheimer's patient a technique to help enhance word recall. So it was an expanded rehearsal technique. And immediately after being taught that technique, this individual's recall ability improved, and it improved dramatically. So measuring this stable baseline in advance helps us be pretty confident that this is the natural behavior. And the only major thing that we're changing in their environment is introducing this one new treatment at this specific time. And we only see a change in that behavior. We only see a deviation from baseline when that treatment has been introduced. So this gives us a little bit more confidence that this change is due to the treatment that was introduced and not something else. So this lets us rule out the explanation of maybe spontaneous change or regression to a mean or something like that, because we had a stable baseline. And then if we wanted to be more certain of our generalizability of this idea here, or if we wanted to be more confident in making a causal claim, we could use replication to be more certain of our both internal, I guess, and external validity in this case. We can look at multiple baseline designs. So this is kind of a variation of what we just saw, where you create a baseline for individuals, but you're going to use a couple of individuals, and the researchers stagger the implementation of their intervention or treatment across situations or times or contexts. So in this particular example, researchers were looking at 3 different children who had autism. And children with autism tend to also be afraid of dogs. And so in this case, we're looking at our dependent variable, which is the distance they are comfortable being from a dog. So the higher it is, the more afraid of dogs they are. So the baseline for this one individual, who they have named John, because they don't use real names. The baseline is fairly high. They had one day where they got closer to the dog, but for the most part, they stayed fairly far away. So that's baseline for John. Baseline for Sally was established not the first set of 5 treatment sessions, but the second set of 5. So after 10 treatments, so they got 10 sessions of baseline. And her baseline was lower, but still she wasn't super comfortable being very close to the dog. And then the third person, Bob, he got a baseline again. So they're not quite stable baselines because this one is showing a decrease here, but we are seeing that baseline is still fairly high. And again, we see this staggering where treatment started. So John had treatment first, then Sally had treatment, and then Bob had treatment. And that's what this first dotted line is showing. In the middle here, we have contact desensitization plus reinforcement, which is basically their fancy way of saying that they had a therapist sit with the children, and they would ask the children to go closer to the dogs and distract them by playing a video game and ask, could we move closer? And if they did move closer, they would get their favorite snack. So they were rewarded for moving closer to the dog. And in each case, the children were able to get closer and closer to the dog up until the point where they could pet the dog. And that's where this line here is sitting right at the bottom. So they got very, very close to the dog. And so both John and Sally were able to pet the dog. Bob did not, but even being, say, 5 feet away from a dog is much better than only being 25 feet away from a dog. So we're still seeing improvement. And then they also included a measure of generalization, which was if they saw dogs in a new environment after the treatment, how close did they get? So if there was a dog in the hallway, would they walk up to it and pet it? And in most cases here, they had yes. So some evidence for improvement and effective treatment. So now we're seeing it across multiple cases with multiple baselines, and the baselines were staggered to help us control for any external forces that might be driving this pattern. We can also have, so for the last example would be a reversal design. And in this kind of setup, the researchers will observe a baseline of behaviors. So here, again, baseline at the beginning, and then they will enact their treatment. But unlike the others, where they would have baseline and then treatment and then make a conclusion, here they would withhold treatment for a period to see if the baseline responding returned. And so in this situation here, they were looking at an individual who would ruminate, which basically means they would regurgitate some of their food. And so this individual, when left to their own devices, would ruminate fairly often. But when they were given a treatment, which was basically to offer them their favorite foods and mostly distract them, they would ruminate less. But when the researcher wasn't there to offer distraction, to encourage them, and to give them food, the rumination would resume. And so they reversed sort of no treatment, treatment, no treatment, treatment, back and forth a bunch of times, showing this pretty steady pattern. And so the more reversals they have here, the more certain they are that it is the treatment that's causing these changes. There are some limitations to this design. So for example, it might be unethical to withhold treatment from an individual. So to take away treatment afterwards might not be ethical. So in some cases, you can't withhold treatment. In other cases, sometimes the treatment is something that permanently changes the participant. So if you're using some kind of learning skill, like what we had talked about with the individual with Alzheimer's, learning to recall words, you can't ask someone to unlearn a task so the participant is forever changed. So there are some restrictions to this one, but it is a fairly telling design here. And you can't talk about small n studies in psychology without touching on a couple more of the big names. The first of these was Piaget, who was studying cognitive development in children. And most of his theories are basically what founded developmental psychology that we have nowadays. But most of his theories were developed because of careful observation of his own children. So he was famous for his idea of conservation of liquid or conservation of volume, where younger children assume that a taller glass has more liquid in it, even if the volume is the same as a smaller glass. But as they get older, there's a predictable period in which they understand volume. And so they will be fooled by a tall glass versus a wide, short glass up to a certain age, and then they figure it out. And that development is very predictable. So there's lots of developmental points that Piaget had figured out. And even though he had a very small n with only 3 children, he had very careful and systematic observations. He used very well-defined constructs, and he replicated his results extensively using multiple methods across all of his children. So a lot of his research was still fairly sound despite having a small n. And the other big name for small n's in psychology is Ebbinghaus, who was famous for his forgetting curve. So he was an experimental psychologist, and he was conducting memory studies. So the interesting part here, though, is that his n of 1 was actually himself. So he made himself memorize long lists of nonsense syllables, and then documented how many syllables he remembered at different time intervals. So how many did he remember after a day, after 2 days, and so on and so forth. And so this is what one of his curves looked like. And so again, his studies had an n of just 1, but he used precise experimental control and measurement and lots and lots and lots of replication. So these studies are still important to the field. So just examples of how an n of very small quantity can still be useful. And for whatever reason, I forgot to change the title here, but this is a summary of the 4 validities for small n experiments. So internal validity in these cases, the ones or the examples that we've talked about for small n have all been very well documented studies, or well documented and well constructed. So the internal validity is very high, especially in the examples we've talked about, because they are well put together and carefully designed studies. So just because you have a small n, or earlier on, just because it's a quasi-experiment, you don't always end up with internal validity problems. Especially with these small n designs, you can get around internal validity issues by being very precise and careful in your setup. For external validity, this can be problematic. It's easy to question external validity with small n designs because it's hard to apply an n of 1 or 2 or 3 to an entire larger population. But we've kind of talked about with experiments that sometimes the goals of the research isn't always generalizability. Sometimes we will sacrifice external validity for other factors. Maybe we care more about internal validity. An example would be some medical studies. If you're treating a very, very rare disease, then maybe you only care if your results apply to other people that have that disease. You don't necessarily care if your results apply to the broad population of human beings. So external validity and how much you care about generalization will depend on what you want to do with the results. And you can also have ways around that, so you can help maximize your external validity by comparing results of one study to the results of other studies. The more replication and the more congruence with other studies, the more confident you can be that you can generalize. So it's not always going to be a problem. For construct validity, no matter what study you are conducting, whether it's small n or experimental or any of them, you're always going to care about defining your variables well. So construct validity is going to be fairly straightforward. If you define things well and you're making good, precise observations, then you can have fairly high construct validity. And if the things that you are measuring are sort of difficult, if they're sort of abstract things like how close a child gets to a dog, or feelings or emotions or something like that, then maybe you can use multiple observers, check for inter-rater reliability, watch out for biases, and all the things that we've talked about in relation to other types of setups. And for statistical validity, this is where we get interesting. So due to their unique design, due to small n studies having small n's, they really can't use traditional parametric statistics. So you can't run a t-test on an n of 1. So in a lot of cases, you don't really get statistical validity because you can't run statistics. In a lot of cases, you're going to be lucky, and maybe the effect is going to be so strong that just looking at the results, looking at the fact that HM can't remember that he saw something, and the fact that anyone with a functional hippocampus recognizes that they saw something, tells you that there's something going on. But you always have to be careful to treat the data appropriately and to keep in mind your limitations when drawing your conclusions. So statistics with small n's are weird, but when you're running these kinds of studies, you're aware of that weirdness and you adapt accordingly. And that is it for chapter 13. We have one more chapter left, and I will see you in that lecture.